Hi there. Can you hear me? Okay, great. Now that Idma and I am co-hosts, we can proceed this session as well. Hi, everyone. Idma, I can't hear you. Can you open your mic?
Now it's open?
Yeah, that's okay.
Okay, for some reason it was closed.
Okay, so we're going to talk about the supernova here, a little bit of cosmology for an introduction for the Thursday, I think. And I will be speaking later on. So Inma, it's your turn.
Okay, thank you. Tell me if there is something you don't understand, or well, you tell me through the chat or whatever, or at the end.
Okay.
Thank you. It's a great pleasure for me to be here with you. Thanks to all participants for attending. And I have changed a bit the title of my talk. I will focus on the application of Taiwanese supernova to cosmology, because this is nowadays a very active area of research. I am at the University of Granada, and I am also a member of the board of the Azarquiel School, as you know. And I cannot change. Let me. I cannot pass. I don't know what happened. It seems that I am frozen. Can you hear me?
Yes, we can hear you.
But I cannot. Now. Well, I don't know what happened. It was like frozen. Okay. Once more, I would like to thank all the local organizing committee for the great job they have done to have all of us here celebrating the school. And especially, I would like to thank Professor Orhan Golbasi and Aysegul Teker Yelkensi. And of course, also the ID University and the Turkish Astronomical Society for their support. And let me share some photos of my city. We have an online school. I would like that you feel closer to me and to where I live. So this is the Alhambra Palace in Granada. Here you have some more pictures. And the photo down is the area called the Albaicín. Here is where we celebrate the first Azarquiel school in 2010. And here in this parish where I live. In Granada, we have also the madrasa that was built in 1349 by Yusuf I, and astronomy was one of the subjects in the curriculum. On the wall, we can read some inscription like this, saying that make a study shine like a star, that I think is a good inspiration for us, for the school, and for everyone. The school, as you know, is named in honor of one of the most famous one of the Andalusian astronomer, that is Azarquiel or Azarcali. But at that time, astronomy was relevant in the society and for the governments, and there were many astronomers in Al-Andalus. Here you have some of them from the 11th, 12th, and 13th centuries. Okay, let's start with the lesson. To a great extent, cosmology, in particular the dynamic of the universe, is based on our ability to estimate distance. So we have to know with our how far are all these points, and based on this, we will see we could estimate some of the cosmological parameters. The first step in this direction, one of the most common and strong and simple also methods to estimate distance is the standard candle. as you probably know, if we know the light emitted by our source, we know the luminosity or the absolute magnitude. As far as we are, the dimmer we show this light, and then we can estimate the distance. This is what it is well known as the distance modulus of the luminosity distance, in which, of course, it's critical to be sure that we know the luminosity, the absolute magnitude, and that we know the apparent magnitude with our detector. Of course, we have to correct for the distinctions and any other absorption, whatever that we have on air atmosphere of our detector, to be sure that we are speaking about the apparent magnitude of our object. The first step applying this method and doing important a contribution to our knowledge of the universe was taken by Henrietta Swan-Leavitt. She was studying in photographic plates a type of variable star that you probably know, the C-phase variable, and she realized that there was a relation between the period of this star and the luminosity. So it was possible to link the luminosity, so the absolute magnitude, with the period of this variable star. So you know the period, you know the luminosity, and then with the apparent magnitude, you can estimate the distance. Now this period luminosity relation is called the Leavitt law in honor of Henrietta, the discoverer, Henrietta Leavitt. And thanks to this law, it was possible to know the size of our galaxy and to do some important steps in our knowledge of the universe. At the beginning of the 20th century, there were several observations about telling us that most of the galaxies around us were receding from us. The fact that they were receding was already explained yesterday by Tahani Maki, and she also told us about the redshift, the displacement of the wavelength, and the relation with the velocity. This is for velocities smaller than the velocity of light. You have to use the corresponding relation for relativistic velocities. And so there was this observational fact that most of the galaxies were receding from us, but it was thanks to the period luminosity relation that it was possible to associate the distance to these galaxies. And in this way, the nowadays known Hubble-Lemaître law was proposed, in which we have a proportion between linear dependent between the velocity and the distance of the galaxy, and the slope of this relation is the Hubble constant. You see here the original plot from Hubble, in which we have here the velocity, here the distance, and if you try to compute the slope, here is quite a visual note that you have the 5 kilometers per second per megaparsec. And this was at the Hubble time. Of course, in the context of the Big Bang and the general relativity, this redshift is interpreted and is understood as the change on the scale factor of the universe. And we take for the current time, for redshift 0, we assume the scale factor is 1. Surface can be seen to a certain distance, but if we want to go further and to estimate a distance to extragalactic source or to this galaxy, we have to use a more luminous standard candle. And our better standard candle nowadays, it has been so for a long time, are Type 1a supernova, this thermonuclear supernova we are speaking about. This is because they are very bright, so we can see them very far away, and also they are very homogeneous. As the surface, they are not equal, they have to be calibrated to estimate the distance, and in fact, here you see several light curves of Type 1a supernova at the time of the maximum light, that here in the peak, this is the peak area, and you see that they are not equal, but there is a relation between the maximum luminosity and the decline rate of the light curve. This relation is in this sense in that brighter supernova decline slower, dimmer supernova decline faster, and this was realized by Mark Phillips in 1993, and he proposed a calibration relation based in the magnitude that the supernova decreased within 15 days after maximum, this delta M15, and there is a relation between delta M15 and the maximum light. Also, the brighter objects are bluer, the dimmer objects are redder, and if we add the color to this relation, we increase the precision of the calibration relation. So for type 1a supernova, we have a calibration, instead of in the period, like the period with this effect, we have a calibration based on the light curve peak, on the decline rate in this case, and the color. There are other calibration proposed. Still, there are some new calibrations, because one of the important steps is to increase the precision of this calibration in type 1a supernova. So when we go to a galaxy, which we are looking at supernova in a faraway galaxy. Here, for example, this is the supernova, I didn't tell you before, and you see the luminosity is of the same order of the galaxy, the galactic luminosity. When we observe this supernova, if we have this decline rate, we can infer the absolute magnitude. And so doing this in the local universe, with supernovae in galaxies where we know the distance, is possible to obtain this relation we were talking about. And for example, if we see that the magnitude in the first 15 days decline by 1 magnitude, then we can say that the supernova, the absolute magnitude in the blue in this case, is minus 19.4, for example. And in this way, we can construct the Hubble diagram. Of course, in all this game, it's important to increase the precision, because the precision we have in this calibration, that in this case is smaller than the dispersion in magnitude, is smaller than 0.2 magnitude, the precision we have translating the precision we have in the extragalactic distance we estimate, and it will also translate in the estimation of the cosmological parameter. Another important thing is to control all the systematic effects. We have now more and more objects, so statistical effects are not a problem, but a possible systematic effect, as it could be an evolutionary effect, that is the nightmare of all the standard candle, is one of the main concerns. I mean, if, for example, the supernova in the local universe, from where we had this calibration, were not equal to the faraway supernova, for the supernova that occurred several gigayears ago. The theoretical model proposed to explain type 1a supernovae agrees very well with this idea of the standard candle, because the most common accepted scenario is that type 1a supernova are the thermonuclear explosion of carbon-oxygen white dwarf that accreting mass from a companion in a binary system reach a mass close to the Chandrasekhar mass. And when they are close to this mass, they compress and they reach the conditions for the emission of carbon in the center. And then we have the explosion of the whole white dwarf. It is important, I would like to remark, that we don't arrive to the Chandrasekhar mass. If we were arriving to the Chandrasekhar mass, then we would have the collapse, and we will have a core collapse supernova, not a type 1a supernova. So we are close to Chandrasekhar mass. Due to this, the white dwarf compressed, and when it compressed, it reached the temperature and density needed for carbon emission in the center in this white dwarf that is in the degenerate condition, and this caused the explosion. In the explosion, several nuclei are synthesized, in particular iron peak elements, and among them the radioactive nickel 56. And it is the decay of nickel to cobalt to iron, this energy, radioactive energy, the energy that powers the light curve. This is very important because I was showing before, the light curve is an important piece in our cosmological application. And also the luminosity at maximum, that is an important piece, is proportional to the nickel 56 mass synthesized during the explosion. Around half a solar mass of nickel is synthesized. So this model, as you see, we have always a carbon-oxygen white dwarf with the same mass that explode give very good support to the standard candle idea. And this model explains properly most of the observed property of Taiwanese supernova, like we don't have hydrogen in the spectral maximum time. We can find Taiwanese supernova in galaxies where star formation finished several gigayears ago. We can control the light current in several bands. We can reproduce the spectral evolution because this Taiwanese supernova, the Jesta, is expanding at several thousand kilometers per second. So it's transparent, and we see inside no, when after in the explosion. And so we are able to reproduce also the spectra in different, the infrared in the optical. So we are very confident about the theoretical model, although there are still some open questions. Supernovae, for this reason, has been used for cosmology, and in particular to estimate the Hubble constant from long ago. We have here a work by Koval in the 1968. At that time, the Hubble constant was estimated to be 100 kilometers per second per megaparsec. This was when all the supernova were assumed to have the same maximum magnitude. And after the calibration relation was established, we have more precision. And this is also Hubble diagram with supernovae, another supernova in this area, this distance, but we have also other standard candle in this area. And we have also, like before, velocity and distance. And in this case, the Hubble constant estimation is above 72 kilometers per second per megaparsec. If you remember, probably no, because I was fast passing that slide, the Hubble diagram, the original Hubble diagram would be here, no, in the center, because you were like 1,000 kilometers per second here and 2 megaparsec here. So we are going much more further, thanks, of course, to the new instrumentation and to detector like the CCD in our telescopes. If we go to higher redshift, we can start playing with more cosmological parameter. We can estimate this cosmological distance, and this part was very well explained yesterday by Tahani Maki, and also Oscar has referred to these questions, and Mark Bastero next Friday will also speak about cosmology. So I will just revise some concepts that probably you know. The expansion rate of the universe is not constant, it depends on time. And this is the Hubble parameter, in which we have the scale factor of the universe that is related, as we said before, with the redshift. We can also define the deceleration parameter, Q. This deceleration parameter has a minus sign here to make it a positive number when we have deceleration. This is an historical reason, because the idea was that the matter in the universe was decelerate the expansion. So it was expected that the expansion rate of the universe after the Big Bang was going to be decelerated due to the presence of matter, dark matter, baryonic matter, whatever, things that make gravity. So this is the reason, the minus sign. And also we can relate the Q parameter with the content of the universe, here expressed with the density parameter depending on matter, a relativistic particle, and I have already added here the cosmological constant or dark energy. And this component has an equation of state related the density with the pressure that Oscar was speaking about when radiation dominated at the beginning of the universe. Later on, radiation dilute, so it's not more important. And we will have the matter that dilute with the scale factor to the -3. And of course, the cosmological constant, where constant of the dark energy has a density parameter that is constant, we will not have any change. And also we can then know the geometry of the universe that is related with the total contribution of matter, radiation, and dark energy, for example. These parameters are normalized to the critical density. And if it's 1, you know, we speak about one flat geometry. If it's greater than 1, it's a closed universe, and is smaller than 1, is an open universe. What can we do observationally? Observationally, we can compare the current expansion rate of the universe, the Hubble constant, with the previous expansion rate. And how would we do this? The idea, the beginning was, as I said, to estimate how much the expansion was slowing down, was decelerating due to the presence of matter, and to obtain from this deceleration the amount of matter in the universe. So I think this plot was also shown yesterday by Sinan, no? And here, for example, this is today. This is the scale factor of the universe. This is going back in time. This will be the future. If the universe was empty, we will have a constant expansion. So this is what we expect. So we will compare with this, what we expected from an empty universe, with other type of universe. If the universe is slowing down because of the presence of matter, that's gravity, as I showed, the expansion will slow down. So for the same change in the scale factor, that is for the same redshift, the object, our standard candle, will be closer in this type of universe compared to this one. So the groups that were setting these surveys, they expected that they were going to find closer supernovae that is brighter than for a given redshift than what was expected for an empty universe. But what it was found was the opposite. It was found that for a given redshift, that is for the given redshift, that is for the change in the scale factor of the universe, for a given redshift, the supernovae were dimmer, that means farther than what you expect for an empty universe. And this means that the expansion of the universe is accelerating, no? Is the only way to obtain an acceleration. And an important consequence is that you can see here, but I will do also an example, is that an accelerating universe is older. So if it is the Big Bang and we are here, we will have an accelerating universe. More time has passed since the Big Bang. But this is not very intuitive. I will say that it could be anti-intuitive. I will make an example, because we could think in principle that a very fast expansion, we will arrive to the scale factor, current scale factor, in a shorter way. We have acceleration, but you have always the key point that you have always to be here in the current universe and look from here. So, for example, suppose that we go from Uruk to Byblos by car. That would be around 1,300 kilometers, and that we arrive at Byblos at 100 kilometers per hour. If we have traveled at constant velocity, that would mean that the trip is 13 hours. But if we arrive at Byblos at this velocity, but we are braking, that implies that we were moving faster before. This implies that the time is less. And we arrive at Byblos accelerating, and we arrive always at this velocity, but we arrive accelerating. This implies that we have moved slower before. And then this means that it took us more time since we left Uruk. Translating this to Hubble diagram and to the observations, we have here the distance modulo, the luminosity distance, and here again the redshift. We don't have problem with the redshift because the redshift is the displacement of the spectral line in the spectra. You know, we have more problem. May have more problem here in these Hubble diagrams. in this direction, we have dimmer, that means farther source. And in this direction, we go, higher redshift, we go back in time. Usually, we represent a relative distance, and that is that to emphasize the difference between different cosmological models, that I will tell you, we put all the model with respect to a reference model that usually is taking an empty universe, which is constant expansion. So, for example, here, as you can see, different contribution of matter, and including or not the cosmological constant, would imply a different behavior of our standard candle. So this, and what was expected, as I told you before, in the 90s, it was that we were going to find our standard candle showing this, that is a flat geometry, all matter with the universe slowing down. Okay, here you have the expression for the luminosity distance in function of the current content of in matter, all included, dark matter and baryonic matter, and the cosmological constant. We don't have the relativistic particle or photon because they have dilute and they are not more significant. And depending on the geometry, you change this function. And I remember that the deceleration parameter is written in this way. So, of course, a universe only with matter, we will have, if it's one, we will have 0.5 of the deceleration parameter, positive, that means breaking, decelerating. And if we want to accelerate the expansion, the only way is to have here a minus sign, so a component of the universe that counterbalance this part that makes the gravity. And in fact, as I was telling you, what was found for two different groups, the Supernova Cosmology Project and the High Redshift team that were working independently, was that the supernova, instead of in this reproducing that model, follow this order, in which the dark energy or cosmological constant is required to imply acceleration, and the density parameter is matter parameter is 30%. And here you have the light curve of the supernova redshift around 0.5. That is one of the supernova that was included in this work. To put these are draws, but if we go to the real data, we have here the sample of these two teams, the High Redshift team and the Supernova Cosmology Project. Here we have the usual Hubble diagram. Here we have the Hubble diagram represented, as I told you before, with respect to an empty universe, to emphasize the difference between different cosmological models. And the discovery was that a redshift between 0.3 and 0.8 supernova were around 0.2 magnitude fainter, that means farther than what we expect for an empty universe. This implies, and there is no other way, that the expansion rate of the universe is accelerating. And for accelerating the expansion rate of the universe, we have to include a component that compensates all the gravitational effect. So we could say like a repulsive component making a negative pressure. So for this discovery, these two groups obtained the Nobel Prize in Physics in 2011, say for the discovery of the accelerating expansion of the universe through observation of distant supernovae. I recommend you to read the two papers, the popular one and the more scientist one, that are in the webpage of the Nobel Prizes. They are very clear and I think very well written. Here you have the Saul Perlmutter, who won the Nobel Prize for the Supernova Cosmology Project, and Brian Smith and Adam Rees, who from the High Redshift team, who also won this Nobel Prize. So, this, of course, to introduce this component in the universe was something very exotic somehow, but it was very well accepted because in cosmology, the introduction of this dark energy or cosmological constant parameter led to a concordance between different independent astronomical observational observations. Here we have a plot that is also very common. We have the density parameter of the cosmological constant or dark energy, and here the matter, as I say, all matter included, including various cold dark matter. And here we have what the observation from the cosmic microwave background implies, before with WMAP, later with Planck. And the cosmic microwave background implies that we are close to a flat geometry. This could mean that the total density parameter is close to 1. At the other side, the large-scale structure or baryonic acoustic oscillation, gravitational lensing, all the observation that indicates gravity led to a density parameter of matter around 0.3, 30% of the critical density, let's say. So this is all that is doing gravity. And we have like here. And of course, if these two were right, then 70% was missing and couldn't be something making gravity. And then the supernova arrived, implying that we need an acceleration of the expansion. This means a negative Q. And with this, implying this area here. So as you see, the supernova, even for an empty universe with no matter, with zero, needs acceleration, and agrees with the other two around these values of 70% or 30%. Well, you may listen more or less than 70%, and here more or less than 30, but still in these, the values are around here, and I will speak about this value. With these values, the acceleration, that is an acceleration, is around, you put just here 0.3 and 0.7, you take around minus 0.6, and this implies acceleration. And the universe is, as I said, older than for an empty universe, and it would be around 14 gigayears. And this is in agreement with the age of the older globular cluster. That was one classical problem between the stellar evolution and the estimation of the age of the globular cluster and cosmology before. So you will have seen also this similar plot in the Oscar talk. The standard model for cosmology, what is called the lambda cold dark matter, is called lambda cold dark matter because most of it is lambda or dark energy, and the rest is matter. But from this matter, a big percent, the majority, is cold dark matter. Only around 4 or 5% is baryonic matter. So our universe has this nowadays, so this is the current universe, has experienced a recent acceleration. It has a geometry close to flat, but we are left with a 95% of the universe unknown, as we don't have still a detection of the cold dark matter components, and we don't know what is the dark energy. So you may think if it is all done. So we know, we have speaking about the Hubble constant, we have speaking about the dynamic of the universe, we know about the acceleration. If we go still further, and here you can see several supernovae at redshift, as you see here, 1.4, so greater than 1, most of them. If we go further, we can explore what happens even before in our universe, in the dynamic of the universe. And going to redshift up to close to 2 with Taiwanese supernova, with the Hubble diagram of Taiwanese supernova, we have also observed the recent transition from the previous deceleration of the expansion to the recent acceleration of the expansion that we were speaking before. And this is claimed to be established at the 99% confidence level. We can see here, again, a Hubble diagram relative. So with respect to an empty universe, that is this green line. So the green line is constant expansion. Everything up is objects that are dimmer, so farther, so means acceleration. Everything that is down are objects that are closer, brighter, so implying deceleration. And we have several lines for several cosmological parameters. For example, this would be total density of 2 or 1, but all matter with matter, and this density model, and these two lines include the dark energy. So what we observe here is what in fact is expected for the number we were showing before. So a universe with 70% of dark energy and 30% of matter would be dominated before by the matter, so we will have deceleration, and recently it came dominated by the dark energy, implying acceleration. So if this is the equation of a state, for example, for any component of the universe, in particular for the dark matter, dark energy, sorry, for a vacuum energy, or for the dark matter being, for example, the vacuum energy or cosmological constant, we will have here -1. So this would imply that the cosmological constant, the density parameter is constant with and does not dilute with the expansion of the universe. And in fact, we can, with this number, compute with the equations that Tahani Maki was showing yesterday. We can compute at which scale factor of the universe or redshift the transition from deceleration to acceleration happen. And with this number, we will obtain that the transition happens for when the universe was around half of the present scale, and the redshift around 0.7. So we expect from this model, for the lambda quantum matter model, with these two numbers, this transition from deceleration to acceleration at this redshift. So our present idea to have a picture that is easily to see, we will have here the Big Bang. At the beginning, we have the radiation domination, but soon we have also the matter dominated era. We have for all these the deceleration of the expansion, and at this time we have a transition from deceleration to acceleration, and we will have the acceleration of the expansion due to the fact that the matter dilute with the scale factor to the -3, so it becomes less and less important, and the dark energy take over and dominate. And we have observed supernovae up to this time and a bit further, so we can check this behavior in the dynamic of the universe. So what is net? I will tell you now about the current areas of research. One is concerned the Hubble constant. Nowadays, there is what has been called the Hubble tension, because the value of the Hubble constant obtained by the cosmic wave background, in particular by Planck, that refers to the early universe, is around 67 kilometers per second per megaparsec. So here we have, let me show this plot. This plot that you have here, you have the Hubble constant. This is 65 to 80, and the cosmic wave background indicates values around here, this pink line. While the Taiwanese supernovae that we are exploring the more recent universe give us values greater than those for the cosmic Milky Way background. This is if we look that if we use for calibrating Taiwanese supernova C phase, or we use the tip of the red giant branch, that also Oscar was mentioned for the question of the actions before, we have different value of the Hubble constant based on Taiwanese supernova. And this you can see here, the area of the Taiwanese supernova is this, and this is the values with the C phase calibration, and these are the values with the tip of the red giant branch calibration for Taiwanese supernovae. And these are other methods that has in general less precision, or there are very few objects in some of them. One important thing to mention is that the cosmic Milky Way background is an indirect method, because we have several parameters, and we have to fix all these 5 or 6 parameters at the same time. And while Taiwanese supernova, we have seen, is a direct method, because we track in the Hubble diagram, we have directly track of this dynamic of the universe. So this is one of the, as I said, this is one of the most important questions today in cosmology, to finally estimate the Hubble constant and to solve this so-called tension in the Hubble constant. And the other, of course, is to explore what is the nature of the dark energy. It has been said that this is the most profound question in science today. It could be, as I mentioned, the energy of empty space, the quantum vacuum. It could be a dynamical energy field. It could be a modification of gravity at large scale. I think Mark Bastero on Friday is going to speak about some of these possibilities. And this is, as we were showing before, our current idea of the universe, in the sense that we had the Big Bang, we had the deceleration due to matter, we had the acceleration due to dark energy. We are around here, and we don't know the future of the current, the dynamic of the universe, unless we know the nature of the dark energy. And what is being done now, and this is also very active area of research, is to try to put constraint on the question of state of the dark energy. This is the question of state, as I said before, density related with the pressure. And if we assume a flat universe, so we assume that the total density of the universe with all the components is the critical density, and we assume also that this parameter is constant, we can construct this diagram in which we have now here, as before, the density parameter of the matter, all included, dark matter and baryonic matter. And here we have this constant of the equation of state of dark energy. And Taiwanese supernova, the baryonic acoustic oscillation, the cosmic Milky Way background indicates a value that is very close to -1, as we expect for a cosmological constant or for the vacuum energy density. Of course, one of the questions is if we have enough precision to detect different things. And here I have put again what is relative Hubble diagram with different cosmologies, just changing the value of this constant parameter. As we see here, you remember we have in the calibration relation a dispersion of 0.2 magnitude that would be from here to here. So to distinguish these different cosmological models, we will need to increase the precision in the calibration relation in our estimation of the distance by factor of 10. And this is also a hot topic nowadays, to increase the precision on the calibration relation of Taiwanese supernova. And as I mentioned before, at the beginning of the talk, one of the nightmares of all standard candle is the evolutionary effect, that is a systematic effect, because the calibration we have is local, and we are assuming that the supernovae were equal in the past as the supernovae in the current universe we have used for our local calibration. But the observation of Taiwanese supernova are indicating some possible dependence with the population from where the supernova come from. For example, brighter supernova occurs in galaxies where there are ongoing star formation, and in these galaxies, the supernova rate is also higher. And also, after applying the calibration relation in the Hubble diagrams, it could be seen that supernova are brighter in massive galaxies. This possible relation of the supernova with the population where they come from is not simple, not to distinguish and to use as a systematic effect, because we still don't know, for example, in the supernova, which are the progenitor. We have problem with is an open question still, the identification of the progenitor of Taiwanese supernovae and also the explosion mechanism. We know, as I said before, in the theoretical model accepted, that we have the explosion of a white dwarf that is approaching the Chandrasekhar mass. But stellar evolution gives us carbonaceous white dwarf with a mass of around 1 solar mass. So we need, of course, accretion. And this accretion could happen in the so-called single degenerate scenario, where the companion of the white dwarf is a normal star, a main sequence, the red giant, an IGB star, or it could happen from another less massive white dwarf that merge via gravitational wave radiation with the and finally form also an accretion disk. In this both scenario, if both probably are giving Taiwanese supernova, how many supernova come from one and from the other? And there are still open problems also with the rates and with we have enough system given risk to supernovae, and also with the accretion rate. So this is also the identification of the progenitor and the explosion mechanism, and an area of research that we need to know before we can relate the supernovae with the population from where they come from. This is from the theoretical point of view. From the observational point of view, to increase the precision of the calibration relation, apart from the light curve and the extinction, now the stellar mass of the galaxy is also included. For example, here you have again a Hubble diagram we were seeing before, and here we have for the distant modulus, we have a factor related with the color, factor related with the light curve shape, and recently some group add also a factor related with the mass of the galaxy. And there are several groups trying to identify if there are also correlation with the local metallicity of the galaxy with the star formation rate. This would imply, or some of these dependent would imply a relation with the age of the population of the progenitor. Okay, here you see that the number of supernova is continuously increasing, so we don't have problem with the, as I said, with the statistical effect. And in fact, going further, even with all the uncertainties, we can also explore dependent with the redshift or with time of this parameter in the equation of state of dark energy, as it is done here in this work, in which we have more than 1,000 Taiwanese supernovae, and we in this work there are data from supernovae, that is this PS1 from one of the surveys, and the data also from the Planck satellite for the cosmic wave background and from the baryonic acoustic oscillation. And it seems that as I said, that we are close to -1 and with no dependence with time of this parameter. But we would need to increase the precision. So I am finishing. So what is the dark energy? This is the one of the most important questions nowadays. And if you would like to work on this subject and to answer this question, there are several topics related with Taiwanese supernova in which you can work. I have some time not to finish. One is, as I said, the hot topic, to increase the precision in the calibration relation. Other field is the identification of the progenitor, both with observation. We don't have observation opposite to Corcoran supernova. We don't have observation of the progenitor for Taiwanese supernova, and we have still many open questions in the theory. It's important also to understand the pre-explosion physics during the creation phase and the phases that goes before the runaway in the explosion occur. It's important also to understand the open question with the explosion mechanism. We have a detonation, deflagration, a combination, a double detonation. It's important from the observation to continue increasing the high quality in data, both for near supernovae and for far supernovae. It's important to increase the number of supernovae at high redshift. Also to identify correlation between the property of Taiwanese supernova and the property of the hot galaxy, and especially the properties close to the location of the supernova. It's very important and critical to work in the extinction law. There is the extinction to several Taiwanese supernova is not the same as the extinction we know in the galaxy, and this is also critical to understand this. And also there are a lot of work in the direction of doing, now that we have many objects, doing Hubble diagram, for example, only with subsample of supernova, for example, including only Taiwanese supernova in galaxy with no star formation, with the idea to increase the precision, the calibration relation, or to do Hubble diagrams in the infrared that are not so subject to the extinction law. And yesterday, Sinan was speaking about one of the surveys, several of the surveys that are going on. And of course, any other thing that you may think could help in this direction. And this is all. Thanks a lot. I leave you with this nice image of the Taiwanese supernova Renan that was observed, not the Renan, the supernova by Tycho Brahe in 1972. Thank you.
Thanks a lot, Inma. You have really interesting topics there to be discovered. Do we have any questions meanwhile?
Very nice talk, Inma.
Thank you.
I want your slides.
Yes, I think I will give you my slide, and also anyone, if you are going to put the presentation somewhere, I don't have any problem. I'm sorry I was a bit long. I was speaking with Oscar before. We want to tell too many things.
It was a great talk. Yeah. May I ask a general question, which is not related? Just as, I mean, you are an expert giving your impression, I still feel uneasy, despite all what you have said, on the fact that this kind of universe looks very much as the result of a fine-tuning. A flat universe exactly at the border between an open one and a closed one, critically depending on an estimate, a very difficult estimate of the density of how the density compares to the critical one. I have nothing, of course, to object to your professional discussion. I've heard many of these. For some reason, probably because I am too old, but a universe which looks so fine-tuned, well, leaves me a bit skeptical yet.
I know that Mar, because I have listened Mar speaking, I think, speaking about what she's expected to tell us on Friday, that she's going to speak about this question, about this, as you say, why is flat, and yes, how related with the Big Bang. This is more related with the beginning, that with this cosmological constant or whatever. So with the beginning of the universe, you will, why is flat. So I will leave Mar to answer this question, because I think she has a nice plot about that related with the first moment at the inflation, as Oscar was pointing out.
Inflation imply a flat zero curvature, a flat universe.
Yeah.
But
This was one of the argument often used in the past in favor of an inflationary scenario.
Yeah, but it's a sort of circular argument. You think that you don't have any, not yet, I guess, any observational strong constraint or inflation, and you don't really know what kind of energy is introduced in the universe in that moment. Of course, we have ideas, some symmetry breaking occurring there, but that all occurs speculative. I read recently a popular physics book by Susskind, one of the father of the string. He strongly opposes people supporting, say, fine-tuning in the universe, in particular the anthropic principle. And he says, of course, also this is not demonstrated, but he says that in the view of a universe with many dimensions, you might expect also many big bangs or little bangs. It is a multiverse in which all things that looks strange, well, the fine-tuning of the velocity of light and so on, can be explained simply as the fact that this is one of the thousands or millions of versions of universes. But this does not account for the flatness of the universe. It still requires, as you say, the assumption of inflation. Maybe, of course, I have nothing against. I feel uneasy with such a description, but that doesn't mean it's not true.
Okay. There is one hand.
Yeah, there's one hand. Shashin, as Youssef, is a professor among us. Would you like to speak? You can right now.
Maybe he cannot with the microphone. Or, yeah.
Okay, maybe a guidance.
We'll wait for Friday.
You are welcome. Everyone is welcome to continue discussion with the Slack or and also with me in particular anytime, because I think we are running out of time, and I say
no problem. I mean, but I'll keep it short. I was also interested in how you managed to eliminate that systematic effect, that if the supernovas were not as the same as we thought that they were today, back in bigger Zs, so that you add nowadays a mass effect.
Well, this is a concern, no? It's still a concern. So there are, from the observational point of view, what they are trying to do is to find correlations, as I said, like including the mass of the galaxy, the metallicity, star formation, but it's there, of course. It's not solved. It's there. But it's not important for what has been done up to now. So it's not important for the acceleration of the expansion, because we can keep with this 0.2 magnitude. But if we want to go to understand what is dark energy, then we have to take care also of this evolutionary effect, potential evolutionary effect.
Okay.
But it's an open question.
Yeah, you're right. That's an important issue. Okay, I guess we don't have right now any questions, and we're going to answer that big question at the end after we have the cosmology lectures and the galaxy lectures also on Thursday.
Yeah, I think so.
I think so. And so thank you again, Inma.
Thanks.
Brief lecture. Now we'll be talking about stellar abundances. We have been talking about how these elements have been produced inside the stars and in the first 3 minutes and so on, and how we detect them. That's one of our concerns. And why do we detect them? So I will be sharing my screen now.
Now we see.
Yep, you see.
Yeah.
Okay. I'll try to keep this in this form because I want to see other people as well.
Yes.
Okay. Can you hear me?
Yes.
Perfect. Yeah.
Okay. So I had that one moment of silence, which I thought, what about the unstable connection? Anyway, okay, let's start with the stellar abundances. By the way, you have been seeing me since yesterday, but let me introduce myself. I'm working in Istanbul Kültür University in the Department of Physics, also for the Astronomical Society, Turkish Astronomical Society. And I have done my PhD about the metallic stars and the abundances and the model atmospheres. So in this lecture, we're going to talk about the abundances and the characteristics of a star, the stellar parameters, which are important for the abundances, and line formations also differ and change the abundances. And from lines to abundances, how do we extract the information? And model atmospheres are our main concern. When we talk about abundances, you know, for example, in the sun, the hydrogen has 73%, helium has 25%, let's say oxygen is 1%, and all the others are our concern. And we talk about the abundance of an element in comparison of its abundance according to the hydrogen mostly. And for example, when we give metallicity here as for the sun, for example, it's -2 dex. If it's -2 dex, then the star has 1/200 less iron than the sun. So we also compare it with the sun. If it's 0.5, then it's 3.16 times more iron than the sun. So present-day solar photosphere element abundances are this much small, as you see. So we are dealing with very small numbers, but we have to extract them from the lines. This is the observation we make, and from all of these lines, we have to take them out, information. So it could be a chemical analysis using a curve of growth technique, which nobody does these days. An alternative is a synthetic spectrum technique. But we have to understand what's going on and how does these lines form to get a better result. So to get an abundance, we start with the star's ID. I mean, which spectral type is that? Do we have a photometric classification for that? If there are any assumptions, any estimates that would help to start with. Then we need atmospheric properties. Do we have an effective temperature measured or estimated for that star in any method, or a surface gravity or a metallicity? That would give us the first estimates to start with. Then we're going to follow these procedures where we need model atmospheres. You can use the grids that were made already for certain atmospheric parameters, or you can make your own, which takes time. And then we compute a theoretical spectrum for the assumed abundances for the first estimates. Then we compare the observations, the result of our observations, and these models, and then we iterate simply. So the stellar parameters that I'm talking about is the effective temperature, of course, surface gravity, and the metallicity. We always compare it with the number of hydrogen atoms, and we also compare it to the metallicity of the star among to the metallicity of the sun. How do we determine the first parameter, which is crucial in the analysis, the effective temperature? We need, first of all, some estimates on what can it be. I mean, if you are not observing it for the first time, you didn't find that target, then you should be able to get some, at least satellite values or some photometrical values. So we have multicolor photometry calibrated with stars having fundamentally determined effective temperature. You can start with those, or you can have a low resolution spectroscopy where you can have the ratios of certain strong lines. You can use those ratios to determine, or at least have a guess of the first guess of the effective temperature of a star. That gives us also a first guess for the spectral type. And the effective temperature is determined so that the abundance of an element, well, we usually use, for example, iron element, is independent of the excitation potential of the individual lines. So we need the two different excitation of the same element, and we compare them. Or we can use Balmer lines, sometimes hydrogen lines. The wings of the Balmer lines above, for stars above 5,000 Kelvin, they differ. As you see in this graph, the red line is lower than the green line, so the wings are giving us an idea of the temperature. And well, the main challenge here is recovering the in-string line profiles. If you don't do some good normalization there, then you cannot have the real continuum, and you cannot guess where the real wing is passing. For the hot stars, Balmer lines can constrain the surface gravity as well. So we look at the ratio of iron 2 to iron 1 lines. And in B-type stars, we can also use the hydrogen Balmer lines to determine log G. And late-type stars, we can also use the profile of some strong metallic lines. Could be calcium 2 triplet or sodium 1D doublet. And this is the most frequently used way. But you can also, if there is, you can also use the parallaxes sometimes to guess the G. So we look at ionization balance in the mostly for the iron 1 and iron 2, as I said before. Here, gravity is a free parameter, and by definition, gravity is related with the gas pressure. So in cool stars, iron 1 dominate the species, iron 2 in minority species, and we can have a guess of the log G. You can also use the Balmer lines in some cases where the effective temperatures is even higher than 7,500 for the hotter stars. So log G determines here, as you see in the wings, the outline of the Balmer lines. And the strong lines, the metal lines, can be used for other type of stars, maybe preferred calcium 2 6162 line, or other strong lines can be used for those. Okay, keeping up. So we have to first determine a first guess of the metallicity of the elements. The global metallicity has largest influence on stellar flux. So it's difficult for stars which have a metallicity smaller than -2 dex. and we don't have precision better than 0.23 dex. And for using spectroscopy is easier here. Equivalent width of some strong lines is used. Observed equivalent widths of saturated lines give us the predicted values using thermal and neutral broadening alone. An extra broadening introduced, which means microturbulence and the microturbulent velocity. So we have to take a look at the line profile to be able to measure the equivalent widths. Let me pass these so that we can proceed a little bit faster. So, you know, the spectral lines are affected by some features, and we need enough atoms in the right ionization state. You need enough atoms or ions excited in the right ionization level. So we use Saha and Boltzmann equations in the theory of these assumptions. So the normal natural width would be a Lorentzian profile where we have a broadening. It differs to a Gaussian profile. It could be pressure, collisional effect, Zeeman effect, hyperfine effect, Stark effect when you're dealing with such a line. So we use the Vogt function to determine what's going on there. Hydrogen lines lead us many things. They are the Balmer transitions from the second level. They are the strongest in A stars, and helium lines also are the most abundant element, second most abundant element, and they are detectable only in hot stars and B stars. And line strength depends on level population of the atom. So it is important here, strongest when temperature is low, lines become stronger as the temperature increases, as you know. So the metal lines dominate the FGK stars, and molecular bands also come up in cool stars. So from lines, we have to lead to abundances. We need to relate the intensity or the strength of an observed line to amount of corresponding element in the original stellar gas. For example, we need to find the number of absorbing atoms per unit area that have electrons in proper orbital to absorb the photon at the wavelength of that spectral line. So we use Boltzmann and Saha equations, and they are applied and combined with pressure and temperature of the gas to drive the abundance of the element, excitation and ionization. And however, not all transitions are having the same probability. So here comes a factor of oscillator strength. Each transition has a relative probability, an F value. It can be calculated theoretically or measured in a lab better. And to find the number of atoms lying above each centimeter square of the photosphere, we need that F value. So with those values from the lab, we have a definition for the equivalent width that we can use. The width in weak lines is related with the abundance, okay? Where we have a saturation, the width is directly related with the logarithm of the abundance. And on strong lines, we see it with the square of the abundance, okay? And small weak lines are best for abundance determination. So we don't like the saturated ones. We don't like the strong lines. Weak lines are the best. We can use a curve of growth technique. Well, it's not recently much used, but it is good to understand what is going on. So it's better in the early steps of the analysis to have a look at it. So we use the curve of growth, depend on temperature sometimes. Temperature can affect the line strength. And the curve of growth shape looks the same, only shifted for different values of excitation potential, as you see. And it can also depend on gravity. Gravity can affect the line strength. So it can also depend on microturbulence. The effect of microturbulence is to increase the Doppler width. This saturates the lines. So the strong line is useful to get the microturbulence velocity. Well, it has some advantages, some disadvantages. It's hard to calculate. You'd have to do some lot of calculations and make an initial guess of microturbulence, and you have to take a look at the theoretical curve of growth and so on. And in real life, nobody does it anymore. So it's better to have a spectrum synthesis, a synthetic spectrum. No one ever does no circular throat analysis anymore, but it's good to get to know the topic. You should better do it at least once. So we need for a spectrum which is calculated synthetically, we need a proper line list. That's the critical part of the analysis. Lines need to be chosen carefully, making sure that they have reliable GF values here. If those oscillator strengths and so on are not reliable, are not correct, every parameter shifts. And it also depends on the wavelength coverage also. So what do we need for the stellar abundance? We need an observed spectrum. And we have to normalize the continuum, and we need to measure the equivalent widths. And then we need the model atmosphere combined with these results. Now, these model atmosphere comes from three main sources. Crookes models is the most frequently one used, and prime parallel atmosphere models. It has a very extended grid, so you can find most of the model atmosphere with the parameter that you already looking for. But if there's not, you can also calculate on your own. The Marx models also use the same plane parallel models, and it's also more useful for the cool stars. There are TLUS-D models, which is the most frequently used for the non-LTE model atmosphere and non-local thermodynamic equilibrium models, which are more popular these days. So you need the model atmospheres, and for the line data, for the reliable GF values, you need to go one by one to look up in the laboratory results. Some of the laboratories are making now atlases. NIST atomic spectra database is the most frequently used, or we have the WALD Vienna atomic line database, or HITRON high resolution database, molecular. NIST is the most frequently used, or you can look up to some personal papers. So what we need is a data reduction software for this analysis. It could be IRAF, most frequently used, or instrument-specific pipelines. Nowadays, we also see that these are made already with the pipelines of the satellite observatories, right? And then, but in the end, you need to have a good procedure for continuum normalization. It affects the depth and the equivalent bit measurements, which also affects the abundance analysis. So we can use softwares like Reduce or VLine, which need some experience there. And then we can use code of spectral synthesis, abundance and microturbulence calculations for a code for those. Could be Atlas for model atmospheres and SynTI for synthetic spectrum, width for microturbulence calculations. Those are the Crookes models. And SynSpec could be one of the software that you can use for hot stars, and MOOC even for cool stars. Now, this is how the analysis goes. This is the algorithm that we use. So we have the observed spectrum, we do the reductions, and then we have the line profiles, and then we measure the equivalent widths, and we have a line list. And we combine it with the model atmospheres, and we try to find the element abundance. But in meanwhile, the model atmosphere, first assumptions are going to be in the model atmosphere. So you have a guess first estimates of the effective temperature log G from the literature or some spectrophotometric values that you can get. And then you have the line list, which includes the reliable oscillator strength values from the databases. Then you, with those values, you also calculate a synthetic spectrum with SynthMOOC with like 9 lines. And then you convolve the spectrum and compare it with the one you have, the normalized one you have. And then fix again and find the abundances. And you can use the ionization comparison there for ion 1 and 2, and then the Balmer lines as well for the comparisons. And then you find the abundances again. So it takes some iteration back and forth for the comparison, but it needs to be done in this form. What about the precision? Well, the temperatures cannot be calculated better than 50 or 100 50 or 100 Kelvin. And the gravity no better than 0.102.2 dex. And the microturbulent velocity of a star can't be better than 0.2 kilometer per second. So we have differential abundances. If you're talking about the abundance relative to the sun, you give the precision is 0.04 dex, and absolute abundance is 0.122 dex. We have some problems here. Most model atmosphere use plane parallel models and mixing length and LTE effects, local thermodynamic equilibrium. But there are also non-LTE effects for some, which also changes the issues. Uncertain or wrong GF values can change your abundances. And we also are maybe have to be sure which comparison are we taking. So the number for the sun might be different if you use 3D hydrodynamic models. So how are you going to compare? So what do we learn from these abundances is that we seek to account the production of the chemical elements that we see in the universe, as we have been taught since yesterday. It's time dependence, and for many features of galaxies that we observe, understanding the stellar evolution, the birth and the death of the stars, and how they interact with their environments is central to understanding the evolution also of the galaxies. Okay, that would be it for my lecture. If you have any questions, I'll be willing to answer now or later on. Let me stop. Precision is also a problem in abundance as well.
Not much reaction.
Okay.
One question.
Yeah, sure.
You know, if we are trying to observe, it was told yesterday by Cynthia, I think, yes, a population 3 stars without any metals. Is this possible? I mean, not possible because they are far, but I mean in the spectra, if you have already a metallicity of 10 to the minus 5 or 10 to the minus 6, I suppose you will not see any spectral line of metal. So you will not distinguish 10 to minus 5 from 0. I mean.
I guess not. No, you cannot.
Not.
That would be, yeah, I mean, too small. So how are we going to distinguish them?
No, I think we cannot. Probably we cannot.
Not from the spectra. From some other ways.
And maybe also due to the long time of this low mass star, you will have some gravitational setting of the metal. So even you will observe a metallicity smaller than the real initial metallicity. So I think it's very, well, we will not observe population 3, strictly population 3.
Related with this, I remember, I think too many years ago, I don't remember exactly, speaking with the expert, or with an expert of spectroscopy of supernovae. I asked what is the minimum amount of hydrogen in the spectra that can be seen. This is because you know, Mimma, that this is the way to distinguish between type 1 and type 2 supernovae, no? And in the single degenerate scenario for type 1, it's expected that some hydrogen should be present all around, at least in the more simple model, no, of accretion from a giant or a main sequence companion. And the answer was that if hydrogen is around, you should see it even if the abundance is, the mass fraction is at least 10 to minus 10. So very small amount.
Minus 10.
But this is for hydrogen.
Yeah.
I don't know what happened with metal, with, I don't know, iron or. But for hydrogen, even a very small amount can be seen.
Yes,
Yeah,
maybe.
and despite these difficulties you are quoting, you know, there are colleagues of ours, those looking for the early pollution of the galaxy in materials necessarily produced by massive stars, that apparently disentangle a star that are 10 to minus 7 from those that are 10 to minus 5. I don't know how, you are right, it seems impossible. But I've seen recently that the low mass stars with the lowest metallicity so far observed is 10 to minus 7 times the solar one, which I am not expert, so I really don't know how these things are done. It would be great to look for that.
So of course, I'm not an expert of that, but some years ago, speaking with Patrick de la Vernier, that is an expert of this kind of observation, he explained me that in principle, it's much more easy to derive abundances in low metallicity star than in high metallicity star, because the spectra is much more clean.
Yes, of course it is easier because you have weaker lines. I mean, you have strong lines, weak lines, but it's cleaner. You can see the continuum, which is the comparison point. I mean, so it's easier to determine the line profiles, and everything derives from the line. Okay, let me see here, one in the chat.
No.
Yeah, okay, that's a thank you. Thank you for listening.
Yes, thanks to everyone. Thanks for all the participants.
Okay, thanks for participating in our session. Now we're going to have a short break, I guess. 20-minute break, was it so? Let me check. So, yep, we have here a 20-minute break. And
yeah,
then
half an hour from now.
Okay.
Thank you.
2:10. Thank you. Time for lunch for some people.
Well, it's not half an hour. It's just 20 minutes. So we will be back for student presentations. Okay.
Yeah, but it's at 2:10.
10 minutes earlier. That's why.
Was 2:10.
You finished 10 minutes earlier, I guess. That's why she says 10, half an hour.
Yeah.
10, yes. help us. 2:10. We'll be back at 2:10 Universal Time. Anyway, you do the conversions.
Yeah, okay.
Okay, see you then.
See you. Bye.
See you. Bye.
See you.
Thank you.